Tonight, we're going to explore something that sounds simple, but is actually one of the most mind-bending concepts in all of science. A light year. You've probably heard this term thousands of times. Scientists use it constantly when talking about space. But here's what most people don't realize. When you actually understand what a light year means, when you truly grasp the distance it represents, it changes how you see the universe. It's not just a big number. It's a distance so vast that it challenges our ability to comprehend it. And by the end of this journey, you're going to understand exactly why astronomers need this measurement and why nothing else would work. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. Let's begin with something familiar: distance. You understand distance in your everyday life. You know how far it is to the grocery store, to your workplace, to the next city over. These are distances you can relate to because you've traveled them. You have a sense of what they mean in terms of time, in terms of effort, in terms of what you'll see along the way. A kilometer is about the distance you can walk in 10 to 12 minutes at a normal pace. These measurements work perfectly well for everyday life. If someone tells you the store is 5 kilometers away, you know roughly how long it'll take to drive there. You can picture the journey in your mind. Maybe you'll pass a few traffic lights. Maybe you'll see some familiar landmarks. The distance is concrete and relatable. If someone says a city is 200 kilometers away, you can plan your trip accordingly. That's about 2 hours of driving. You'll want to fill up your gas tank, maybe bring some snacks. Plan for a rest stop halfway. These distances are human-scaled. They fit into our lives and our experience. We've evolved to understand distances we can walk in a day, distances we can see, distances that matter for survival and navigation. But these measurements start to become awkward when we talk about really large distances. The distance from New York to Los Angeles is about 4,500 kilometers. That's still manageable as a number. It's about a 5-hour flight. People make that journey all the time. They cross the continent. They see the landscape change from East Coast cities to Midwest plains to Rocky Mountains to Southwest deserts and finally to the Pacific coast. The journey is long, but it's achievable. It's within human capability. You can imagine making that trip. The Earth's circumference at the equator is about 40,075 kilometers. That's a big number, but it's still something we can work with conceptually. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it takes months. Ferdinand Magellan's expedition took 3 years to circumnavigate the globe, from 1519 to 1522. Modern commercial flights can circle the Earth in about 45 hours if you could book connecting flights that went all the way around. The Earth is large from our perspective, standing on its surface, but it's not incomprehensibly large. It's a finite thing you could, in theory, explore completely. But now, let's go bigger. The distance from Earth to the Moon is about 384,000 kilometers. This is where normal measurements start to feel inadequate. 384,000 kilometers. That's hard to visualize in any meaningful way. It's not like driving across the country. It's not like sailing around the world. It's something completely different. There's no road to follow, no landmarks to pass, no rest stops along the way. It's just distance, pure distance across empty space. How would you even begin to travel that far? The Apollo astronauts took about 3 days to travel from Earth to the Moon using powerful rockets that accelerated them to speeds of about 11 kilometers per second. That's about 39,600 kilometers per hour, roughly 400 times faster than highway driving. Think about that for a moment. 400 times faster than you've ever driven. And even at that incredible speed, which required some of the most powerful rockets ever built, burning enormous amounts of fuel, it still took 3 days. 3 days of traveling through empty space at speeds no human had ever experienced before, just to reach our nearest celestial neighbor. And that's just to the moon, the closest celestial body to Earth. The moon is so close you can see it with your naked eye. You can see details on its surface with a pair of binoculars. It's right there, hanging in the sky. And yet it takes 3 days of rocket travel to reach it. When we start talking about the distance to other planets, to the sun, to other stars, kilometers become completely useless. The numbers get so large that they lose all meaning. They become abstract symbols on a page rather than distances you can relate to in any way. The distance from Earth to the Sun is about 150 million kilometers. Try to visualize that. You can't, can you? Your brain just sees it as a really big number, but you don't have any intuitive sense of what it means. There's nothing in your daily life that prepares you for a distance like that. Nothing in human evolution prepared us to think about distances this large. We evolved to understand the distance to the next water source, the distance to the hunting grounds, the distance we could walk in a day. We didn't evolve to comprehend 150 million kilometers. The Apollo spacecraft that took astronauts to the moon traveled at about 11 kilometers per second on average. At that speed, it would take about 160 days, over 5 months, to reach the sun's distance. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at speeds up to 192 kilometers per second when it's close to the sun, using its gravity to slingshot itself to higher and higher speeds. Even at this incredible speed, which is about 17 times faster than the Apollo spacecraft, the probe still takes months to complete its orbits around the sun. And the star is close. It's right here in our cosmic neighborhood. It's the star we orbit. It's the source of all the light and heat that makes life on Earth possible. We see it every day. It's familiar. And yet it's 150 million kilometers away, a distance so vast that even our fastest spacecraft takes months to traverse it. When we start talking about distances to other stars, even the sun's distance becomes tiny by comparison. The sun is our nearest star, and it's 150 million kilometers away. The next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is why astronomers needed a different unit of measurement. Not because they like making things complicated, not because they want to confuse people with big numbers, but because kilometers simply don't work when you're measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between countries. Technically possible, but completely impractical. The numbers become so large, they lose all meaning. They stop being distances and become just numbers, abstract mathematical concepts that don't connect to anything in our experience. So astronomers came up with something different, the light year. But here's what you need to understand right from the start. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. It's not just a speed limit that we haven't broken yet. It's a fundamental law of physics. The speed of light is a constant, unchanging, the same everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Light travels at about 300,000 kilometers per second. Let me say that again because it's important. 300,000 kilometers per second. Every single second, Light travels 300,000 kilometers. This isn't an approximation or an estimate. It's been measured with extraordinary precision. The exact value is 299,792.458 kilometers per second, but for our purposes, 300,000 kilometers per second is close enough. That's incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in 1 second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. It's a speed that's almost impossible to visualize because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience is an airplane. A commercial jet flies at about 900 kilometers per hour, or about 0.25 kilometers per second. Light travels over 1 million times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour, or about 0.33 kilometers per second. Light is about 900,000 times faster. Even the fastest spacecraft we've built, the Parker Solar Probe, at 192 kilometers per second at its peak, is still only about 0.064% the speed of light. It's moving incredibly fast by human standards, but compared to light, it's crawling. When you turn on a light switch, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in about 10 billionths of a second. That's so fast that there's no perceptible delay. As far as your brain is concerned, the light appears instantly, but the light did travel. It took time. It's just that the time was so short you couldn't possibly notice it. When you see the sun in the sky, you're actually seeing it as it was 8 minutes and 20 seconds ago, because that's how long it takes light to travel from the sun to Earth. The sun is so far away that even light, traveling at 300,000 kilometers per second, needs over 8 minutes to cover the distance. This has an interesting implication. If something happened on the sun right now, if it suddenly changed color, or dimmed, or even exploded, we wouldn't know for over 8 minutes. The event would happen, but the light carrying information about that event would still be traveling toward us. We'd keep seeing the sun as it was, not as it is, for over 8 minutes. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. Not much of a delay, but still a delay. When astronauts walked on the moon and talked to Mission Control on Earth, every word they spoke took 1.3 seconds to reach Earth, and every response from Mission Control took 1.3 seconds to reach the moon. This created a nearly 3-second gap in every exchange. You can hear this delay in the recordings. There's always this pause, this lag, because the radio signals carrying their voices traveled at the speed of light, and even light needs time to cross the distance between Earth and the moon. Light doesn't travel instantly. It has a speed, and that speed, while incredibly fast, is still finite. This is one of the most important discoveries in physics. Before the late 1600s, most people assumed light traveled instantly. You opened your eyes and you saw things immediately, so it seemed like light must be instantaneous. But in 1676, a Danish astronomer named Ole Rømer made a careful observation of Jupiter's moons and noticed something strange. The times when the moons disappeared behind Jupiter varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Rømer realized this was because light took time to travel the different distances. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite right because he didn't know the exact size of Earth's orbit, but he proved that light has a finite speed. Today, we know the speed of light with extraordinary precision, We've measured it using lasers, atomic clocks, and sophisticated equipment. We've confirmed that it's constant, that it doesn't change depending on how fast you're moving or where you are. And we've discovered that this speed, this constant, is woven into the very fabric of the universe. It's not just the speed that light happens to travel at. It's a fundamental property of space-time itself. So a light year is the distance light travels in 1 year at this speed. Let's calculate that. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times 60 times 60 times 24 times 365, we get approximately 9.46 trillion kilometers. To be more precise, it's 9,460,730,472,580.8 kilometers. But for simplicity, we usually just say 9.46 trillion kilometers. That's what a light year is. 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that's the number we're going to try to understand tonight. Because understanding what a light year means is essential to understanding our place in the universe, the distances between stars, and the true scale of the cosmos. But first, we need to talk about what a trillion actually means, because most people have no intuitive sense of how large this number really is. We throw around words like million, billion, and trillion in everyday conversation. We hear about government budgets in the trillions, about billionaires, about millions of people, but we don't really understand the massive differences between these numbers. They all sound like big numbers, so we treat them as roughly equivalent. But they're not. The differences between them are staggering. A million is 1,000 thousands. If you saved $1 every day, starting today and continuing without ever stopping, you'd have $1 million in about 2,740 years. That's a long time, but it's conceivable. You can imagine a timeline stretching back 2,740 years. That takes you back to ancient Greece, to the early Roman Republic, to a time when humans were already building cities, writing books, creating civilizations. It's a comprehensible span of time. A billion is 1,000 millions. Now we're jumping up by a factor of 1,000. If you saved $1 every second, not every day, but every single second, you'd need about 32 years to save $1 billion. That's more than the time it takes for a generation to grow up. If you started counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you'd be 32 years old when you reached 1 billion. Think about that. 1 million seconds is about 11.5 days. That's conceivable. You can imagine a period of 11.5 days. It's less than 2 weeks. But 1 billion seconds? That's 32 years. The jump from 1 million to 1 billion is enormous. A trillion is 1,000 billions. And here's where numbers start to completely lose their connection to anything we can relate to. If you counted to 1 trillion, counting one number per second without stopping, it would take you about 31,700 years. Let me put that in perspective. That's longer than all of recorded human history. Agriculture, the foundation of civilization, was only invented about